Okay, thanks everybody for joining us in person and virtually today for this CISL seminar. The topic is going to be on the joint effort for data assimilation integration, or called JEDI. And we're pleased to have Dr. Yannick Tremolet here. He has a PhD in applied mathematics with his main research interest being data assimilation, methodology, and high performance computing. And he joined the Joint Center for Satellite Data Assimilation to lead the the JEDI effort, which is a collaborative effort between NOAA, NASA, and the U.S. Air Force and the U.S. Navy, UK Met Office, and NCAR to develop a next generation generic data assimilation system for research and operational weather and environmental forecasting. And Yannick also has a background working quite a while with the European Center for Medium Range Weather Prediction before that. So thanks again for joining us today, and we look forward to your talk.
Okay, thank you. All right, so yes, thanks for the introduction. So just to give you a little more, a few details about what the JCSDA is. So we're an interagency collaboration, and our goal is to accelerate and improve the use of, in particular, satellite data for research and for operational applications in weather, ocean, climate, etc. So we have a number of partner agencies, so different branches of NOAA, so the Weather Service, NESDIS, and OAR. Also NASA, especially GMAO. We also have some collaborations with NCAR and the Navy, the Air Force are also members, and the Met Office joined as well, the JCSDA a few years ago. So, everything, the core team is sitting in the middle of all that, and we're trying as much as possible to bring some jointness in the developments for data assimilation in that context. And as far as UCAR is concerned, we are sitting in UCP within UCAR. So the JEDI project, so a joint effort for data assimilation integration, the idea was to have, there's a lot of duplication of effort between all these US government agencies when they develop data assimilation systems. There's a lot of observation processing, definition of observation operators, background error covariances, etc. That's actually very, very similar in all these agencies, but yet we have completely, at the moment, completely different systems. And where they're all basically doing the same thing. So the idea was to bring all that together and develop a unified data assimilation system. Now, we are mostly driven by operational users, and our funding comes from operational agencies, but we also have, as an additional goal, to make the JEDI available for research. So that's, we always have tried to balance these two needs between operations and research. And it's important because there's very often a big gap between, something being developed in academic communities, for example, that never gets transferred to operational centers because we're working in completely different systems and it's too much work to transfer things. So at least we want to make that possible. And then it's up to the agencies to decide what they want to adopt. One point I want to really make about JEDI, it's not about one specific data assimilation algorithm or approach or method. We have a whole list, which I will come back to later, of data assimilation methods in there that people can use and choose from. So that's has always been the goal. And we try to, as much as we can, be driven by the scientific vision for data assimilation, where it is today and where it will go in the future. And we're not trying to save all codes. If all codes are useful, we use them. But if they don't fit what we want, we don't reuse them, and we just scrap them and write new code. So, which is also something that's quite different from sometimes, data assimilation systems tend to have very long lifetime. The current operational system typically are codes that were written 40, 50 years ago, and in the world of computing, that's prehistoric times. we're trying to move away from that. So the general idea for JEDI and for OOPS in particular, which is the central element of JEDI, which is something I actually started back when I was at ECMWF, just before coming here, is that if you read data assimilation literature, you will see expressions like the two I've put here, where people talk about X as the state vector and Y as the observations and H of X as an observation operator and covariance matrices B and R, and they write various expressions with that and various algorithms using these elements. So if you can describe your algorithm using these elements to another scientist in a paper, there is no reason you cannot describe that algorithm to a computer for it to actually run it. So that's the idea behind that design. So we use C++ templates to replace these various elements you see in these equations at compile time by the appropriate, specific implementation that you need for your given problem. So, so it looks like that. We have at the very top here in blue, we have various data assimilation algorithms or applications, and it can be for LIVAR when we started that at ECMWF, but can be DA, can be NKF type. Or it can never be, just a simple forecast. You can think of that as an application if you want. And it uses these green elements, these abstract interfaces. So these are the state is the X I had on my previous slide. The model would be the M operator, the covariances, and etc. And you can write your data assimilation algorithm completely in that layer without knowing which model it will be applied to. And then at a lower level, then you need, when you come with a specific system, so for example, FV3 for NOAA, you need to then implement your state and various, your model and to satisfy the interface that you want there. So usually that means you're taking your existing code and you're putting wrappers in place around the elements that you want to be able to use and call from that abstract layer. If your code is nice and clean, that's fairly easy to do. It's just putting a few wrappers around in the right places. If your code has lots of global variables, that's becoming a problem, and you need to refactor your code so that global variables are not going to interfere with what you're trying to do from your higher level C++ code. So that's typically where, if there is work to do, it's because you have old codes that are based on global variables, and that's where the issue is. Now, what we've added as part of the JEDI project to this is a generic layer where we don't have to implement specific covariances, for example, for every model. We have a collection now of generic covariances that you can choose from and apply, and they will work with any of these models. A few restrictions, for example, for the ocean, because of the shape of the domain, you can't use a spectral representation or things like that. So there's some limitations, but in general, you can use the covariances. You can reuse, I'll go a bit more detail, the UFO, which is the observation operator, the H of X. That's really shared across all the models, and that's really nice. And this YODA element is the interface for observation data access, which I'll come back to. So another way to look at this, it's the same thing represented a bit differently. So OOPS is the object-oriented prediction system. Again, something I started at ECMWF. It's the driver. That's where the data assimilation algorithms are. And it's going to call these various other elements when needed. So SABRE is our system agnostic background error representation. Then you have the UFO, which is the forward operator of the observation operator in data assimilation. And we have interfaces with all the models that are here on the left. So Neptune is a Navy model, UFS from NOAA, GEOS is NASA, MPAS is an MCAR model, LFRIC is from Met Office, as well as the UM. MOM6 is an ocean model. SICE6 is a sea ice model. ROMS is a regional ocean model. So we have all, and the list is actually longer than this, but we are interfaced now with all these models. And to give you an idea here, this graph, these bars represent the number of lines of code in the different repos that we have. And what you see in red at the top is the code that's specific to each model. So it's the interface between, the glue between the generic code and the specific codes. So as you see, there's actually a lot of the code that's the same and that's generic and that's shared across all these applications. And that's really our goal. And we're actually working, this is a little bit old now, this graph. The red portion has shrunk even more than what you see here now. So we're really pleased with that there's a lot of reuse and a lot of commonality between all these applications. So where we are with the observations, you can see here some plots, some examples of the observations we can use. We basically have now the observation operators and everything needed to cover all the observations that are used in operations by all our partners. So if something is used in operations by any of our partners, it's already in, plus a few extra ones that are research type observations that we also have available in that system. And as you can see, it's covering atmosphere, but it's also covering, there's some ocean, some sea ice systems in there. It's not just for the NWP. Okay, so another thing that we did is a generic quality control. So that's one of the examples where when we started this, everybody told us, oh, it's absolutely impossible. You cannot do generic quality control. We all have our little things that are different from each other. It turns out everybody's doing the same thing. They just don't know it, but they're all the same. Here is an example of, in the small font that you see on the left, it's a quality control procedure in Fortran for, I forgot which observation type. We've recorded all that in C++ with this concept of abstract filters. And then you can, from your YAML config file, you can chain your filters and decide which filters you want to apply with which thresholds. And you can specify, for observations that pass or fail that filter, what action you want to take. So you see a few examples there of how you specify a filter for just a small snippet of YAML. So which is quite nice, and it's working. And again, it's all the operational use cases are covered now by these generic filters. Just to give you another example, all these filters were developed for atmospheric data assimilation. When people with the marine data assimilation came, they just took these filters, wrote some YAML files, and they were able to rewrite all their QC without writing a single line of code, just through a few YAML files, which it was also a good validation that we were able to do something really generic that works for all kinds of applications and is super flexible. We had never seen ocean observations before and worked straight out of the box. So you can see here some examples, but it's a really nice tool. And we've extended it now. We have users who are starting to look at space weather, and same thing. They started using these filters. It works for space weather as well. The variable name might be different. Instead of temperature, it's total electron content or whatever we have in the ionosphere, but the code doesn't know about that. Another nice element we have here is the the SABER, so the generic background error covariances. So the way these are built, it's a series of blocks, and we chain these different blocks to build a full covariance matrix. So typically you have a central correlation operator that's in the middle there. And then you build some various transforms you want to apply to your model variables to get to these variables you use in your correlation. So you have some example here. If you start from an AV3 increment, you start on a cube sphere grid with U and V. You can go to psi-chi if you want. Apply some standard deviation there, so you're still in psi-chi in the grid. then you can transform and go to a Gaussian grid, and then once you're on a Gaussian grid, you can maybe apply a spectral transform and do your operation, your correlation in spectral space. So all these blocks can be combined again through YAML files, yeah, so that's very flexible. That's all written in C++, and again, we have a growing collection of operators that we can put there. I would say probably the collection is not as complete as for the observations yet, but again, it's covering the operational needs of our partners at the moment. We have ideas to expand that in the future to do some more innovative stuff, innovative science, which is not necessarily coded yet, but the operational requirements are all met. We were even able to wrap the old, the GSI background error covariance into that framework, and it's wrapped into this, and people can use the GSI background error covariance. And because of that, and because you can put some other blocks around it, if you want to use a GSI background error covariance with a model for which it was not ready for, now that you can build these extra blocks with various interpolations and change of variables, you can actually use it even if in the past you couldn't. So that's nice. Another example of something we've developed, again, that's something that was developed in collaboration with the Met Office, is the idea of a hybrid tangent linear model, where basically, typically the idea is you have a tangent linear and adjoint model to do a 4D var of the dynamics of your model. And the physics is usually a lot of work, and it's more complicated to code because of lots of if statements, lots of things like that don't linearize very well. So the idea of a hybrid TLM is that, so you keep the tangent linear model for your dynamics, but for the physics, you're going to approximate that with finite differences and use that to build a first order approximation, and you can take the adjoint of that and build your tangent linear adjoint based on these finite differences. And then the hybrid TLM is combining your actual TLM adjoint for your dynamics and this finite difference approach for your physics. Put the two together, and you have a tangent linear and adjoint model that you can use in 4D var. And if you update your physics in your model, you just you redo this finite difference, but you have nothing more to code. You don't have this extra burden of maintenance of the adjoint of the physics anymore. So we developed that in collaboration with the Met Office for atmospheric application. But once again, the marine DA people, they came and they saw that and thought, it's super hard to do an adjoint for an ocean model. Let's try that thing. So what they did is that instead of taking the tangent linear and adjoint of a dynamics as a kind of a base on which to build this hybrid, they just took an identity. Just put the identity in there, which means they don't have this base, and just rely completely on the finite difference to do the tangent linear and adjoint, and seems to work really well. So 4D var has traditionally been very difficult to do in the ocean, but here it seems to be working. You can see some improvements there in the quality of the linearization errors compared to the identity, obviously, which is not very good. We're starting to test a few 4D var cases with that. But again, that shows the power of developing something generic, which obviously, in the past would have been developed for super specific to a given grade or a given something. But because we abstract all that away, one person will develop it and others can use it for a completely different application. And many people didn't believe that's possible, but with modern programming techniques, we are in the 21st century. We're not stuck anymore with programming the way it was done in the 1970s, and we can do things like that now. You have to maybe move away from Fortran a little bit, but all this is really doable. Okay, so these are just examples of what we're doing. There will be more developments, all kinds of generic tools that people can use in all kinds of applications. as we go. And then we have also developed what we call Skylab. So it's basically we are applying the same idea, but everybody in their workflow uses the same entities as, as I showed inside the DA. You're going to run a data assimilation, you're going to run a forecast, you're going to go to your next cycle, propagate your background, fetch your observations, etc. So we've applied exactly the same design principle to the workflow, and we have a workflow that's generic as well. The two elements I want to emphasize a little bit here on this slide is the YODA interface for data access. Observations are typically very messy in our world. All kinds of observations, they come from all kinds of different sources. Everybody has their own format, their own layout, their own. So we have this YODA. We put all that into a kind of a common framework. Then we store that into what we call R2D2. So usually people know us because of all the fun acronyms we have. At least you probably have heard that before. So R2D2 is a distributed database. There's a meta database, if you want, in the cloud running on AWS, and we actually store data files in many different places, but we can query that central R2D2 server, and with a fetch command, and it will pick the data where it is and bring it where we need it. So that's kind of the way. And once we have that, we can use these kind of tools in our workflow, and the workflow becomes very portable, and all the complexities with dealing with observations are kind of packed away into these different tools. So that's just a summary here of what I've just described, but that's a common interface for all the observations, so that really we want scientists to be able to focus on science, not on all the technicalities of every data source we can think of. R2D2, we have many R2D2 has two commands, fetch and store, when you want to get your data or you want to push data into that data store, and then it's all taken away. It's software engineers manage that, not the scientists. Those are two different jobs. And, so it's cloud-based. Obviously, some of the data is stored on AWS, but some is stored on specific HPC systems. And we have, on top of that, what our generic workflow is called eWalk. And as I mentioned before, it's the same idea as the general design of OOPS and JEDI, but it's in Python. And we use duck typing instead of templates, but it's the same idea. You write things once. You need a script to run your model, yes. So at the level of a workflow, it's just calling model script. And that has different implementation for different models you might want to run. But the overall structure of your suite that you want to run, the dependency between the different tasks is all the same. There's no reason to change that. Just you're calling a different script when you run it. So it's generic with respect to the model. It's running with a whole bunch of different models: atmosphere, ocean, MPAS, UFS, GEOS, whatever you want. With all the observation types that we have, it's running on a whole bunch of HPC. We've tested it on something like 20 different HPCs. Doesn't mean we maintain it on 20 different HPCs, but at least we've tested it. And it's also generic now. We're working on different workflow engines. So you can use ECFlow as a workflow engine underneath, or you can use Silk now. We are working. It's not finished, the Silk implementation, but it's in good shape. And that's what you get out of that. You can run an experiment with the UFS, which is the NOAA coupled model. You can run an experiment with MPAS, slightly different configurations, but we can ensure through that whole system, and because of the same workflow, the same data store, we have exactly the same observations in the two experiments, and we can do really clean comparisons between two different systems. And you can see the diagnostics are also the same. You have here like UFS MPAS for different metrics you might want to look at in your system. You can see like if you look at the bottom right, for example, near the top of the atmosphere, there's temperature biases that are different between the two models. You can start seeing that. But you can dig into all kinds of things and start comparing, which is something that I've never seen before. Like, I know typically people develop a series of scripts and workflows to run one system, but I've never seen something generic like that, where you can run a whole bunch of different models, different observations in one system, and really have the same plots and compare and put everything. And all these plots go on the web, so you can just go with your browser and look at all the plots. All right, so some examples of what we've done. We use that system, obviously, to validate what we do, to deliver to our sponsors. And it's all configured by YAML, including the workflow. You can choose between different radiative transfer models. So CRTM is the one that we develop, but the Met Office, for example, is using RTTOF, which is a European equivalent, if you want, of CRTM. But we have two now in the system, so you could easily run two experiments with these two, and you can actually choose instrument by instrument. So you can have half of your sensors using CRTM, the other half using RTTOF if you want. In the same run, it's all possible. Again, something that I know some data simulation system in the past that you could swap between the two, but you would swap for all the instruments. There was no choice, instrument by instrument. Now we can really do that. Same thing with GNSSR with 3 different operators, ROP, which is a EUMETSAT thing. We have a UKMO and a NOAA one. And we have all kinds of different data simulation solvers, 3D VAR, 4D VAR, if you have an adjoint, hybrid ENVAR, EDA, various versions of LETKF, GETKF. There's a whole list of them there, different variations on that. So this is just, sorry, I took some slides. They were more geared at people interested in observations. So they were giving examples of what you can do with these filters. You can assign, as you go, different flags, so then you can monitor what's happening with your observations. This is something important for operational centers. They keep track of what's happening with operations, so they can, observations, sorry. So they can detect if a sensor is going bad or something like that over time. It's important for them because it will affect the quality of the forecast. So you can do all these things there. Yeah, I think, if you have questions, I'm happy to go in more detail, but it's the same here, just showing some other examples. So these are some experiments we ran. The NOAA is what we call this commercial data program, where they're purchasing data from private companies, which is a fairly new way of operating for them. They typically have their own satellites and all that. And we've run some evaluation of some of these observations for them. And you can see here different results. Blue is usually good, if I remember correctly. So, reducing the error when you add these observations into the system, which is a good sign that the observations actually have value. And you can see very few red dots here and there. It's not blue everywhere, but overall it's positive. Same thing with sounding balloons. Again, this one is US Air Force as also a commercial data program where they're purchasing data from these balloons, and they asked for some evaluation, which is what we did here. And you can see, how it impacts different things. There's a little bit of red in the stratosphere there, but overall it's still a positive impact. And another example of evaluating private data here was a Tomorrow.io microwave sounders. So Again, I won't go into a lot of details, but if you have questions, we can go into it. Okay, and this is a collaboration we've started recently with the Navy, and that's the Space Weather project. So we're looking here at the ionosphere, and so that's a completely different world for us, something we've never seen before, we're not very familiar with. But where they're measuring electron densities and things like that, the grid of their model, even though it's on a sphere, at the end it's the envelope around the Earth, but they are using this geomagnetic lines to define the grid of their model. So it's kind of folded, goes from one pole to the other, and it's folded at the poles. So it's a completely different structure that we had never seen before, which is often a project to work on. But it's interesting, and we're putting that into the system, and it's going to work hopefully. It's not at the moment we're testing the observation operators, but the goal is to start with an LTKF demonstration, and then probably also do the variational after that. And you can see some references there if you're interested. So the status, really, where we are with the different partners. So you can see the different colors here represent different partners. And you have a different technical readiness level. So 9 means it's ready to go into operations. So at the moment, the Met Office has one system, but at level 9. They are getting a new HPC at the moment, so they're waiting for the new HPC to be in the building to start running that in operations, but they're all good to go. They just have to press a button as soon as the new HPC is in. And then you see the different applications being a different level, like some of them at level 8, so we're fairly close. There are some that are not here, but NOAA is ready. So where it says land, snow, and hydrology, I think it's a 9 now, and it's ready to go. It's going to be part of our next operational implementation. Same thing for the marine, which in GFS 17, which it shows technical readiness 8 on this slide, but I think it's closer to 9 now. And so the system has been picked up by the weather company, and they're using it in operation already. And they did that. We kind of learned about it about a week before they went operational. They did it without us, which proves that the system is usable, and there is somehow enough documentation that we were able to figure out how to use it, how to put it into the system. And then one day we learned, we're going to go operational with JEDI. Oh, great. So the system is fairly mature, I would say. It doesn't mean we're going to stop there. That's only a first step, is to replace the current operational system, but we didn't do all that just to replace the current system and do exactly the same thing. We want to do more science with it. First thing, because we have all the components of the Earth system into the same framework now, we can do coupled data assimilation, which was not, if you look at how the different operational agencies were working before, they had one DA system for the atmosphere, one for the ocean, one for the land, that had been developed by independent teams and had nothing in common. So it was very difficult for them to bring that together and do coupled data assimilation for the Earth system. So now having it all in one makes it a lot easier. So we've started, we actually have a coupled HFX project that's progressing well. We haven't really worked on the coupled B yet. I think some people have looked at it a little bit. And we also have some prototype of a coupled solver. And another big driver for us is to really increase the number of observations that are being used. So I put here this table at the bottom right, where you can see for GOES-R, for example, it's $11 billion, and it's 0.02% of the observations that are actually used in operations. So, there is a lot of untapped information there that we really want to bring that to the next level and multiply the number of observations we use by several orders of magnitude. Because all these observations are there, they cost a lot of money, and nobody's using them. So that's one of our big goals for the coming years, is to really change that by order of magnitude, which does involve some risk. There's computational aspect. More data means more processing. But there's also some science aspect to it, because there is extra correlations you have to take into account to do that properly, etc. So there will be science there as well. And a lot of, some algorithm development, so hybrid TLM is one I've showed. We are also working on optimization, so using cloud computing is one of them, running the data assimilation on GPUs, putting OpenMP. So we're trying to abstract that using C++, Everfoot template of object-oriented programming, but abstract away. For example, we don't want programmers to put OpenMP on every loop they write. We want to abstract that away. We have a way to iterate over the grid point, and we do the OpenMP in there once in one place, and the scientists don't have to worry about it. So we're putting, it's not in the system yet, but we have a prototype, we're putting it in. And hopefully that will be reused for if you want to run your code on your GPU, because then you just change the way you iterate, but you move that to the GPU, iterate over on your GPU. So that's being developed at the moment. Continuous DA is another interesting project we have where it's ongoing. We basically want to keep a data assimilation system running 24/7, if we can. As observations arrive, they are thrown in, and the system keeps every 10 minutes or every hour, often you want, spits out an updated analysis. So that's a completely different way of doing a data assimilation. You completely go away from this idea of a 6-hour cycle, that you do your data assimilation, you stop, you wait 6 hours, you run data assimilation again, etc. So that would be a very different way of doing it, but we have a project going on there. Hopefully that will give interesting results. And of course, AI/ML is the other big thing. How can we use that in the data assimilation? I'll come back to that. Another thing about observations, another big change we're seeing, traditional satellite observing systems are typically big, very expensive, high-quality programs run by government agencies, here in the US or in Europe or in Japan, typically. And what we're seeing more and more is we have small, cheap systems, but many of them. And that means that you can't spend 2 years fine-tuning your data assimilation system for a given platform, because it might not even be up there in space for 2 years. So we have to completely change the way we start working with new observations. And we hope that by having a more, shared system between the agencies, one agency can work on one system, another agency works on another. Not everybody has to replicate this whole process of getting an observation in, n times. If you start having to do it every week, it becomes really a monster that nobody can manage. So hopefully the jointness there will really help to speed up the process and make it more cost effective. Okay, AI models. That's something I'm sure you all heard, that in the last 2 years, AI models became a thing in weather prediction. So we have to adapt to that. So first step for us is to interface with AI models instead of the traditional models I listed earlier, MPAS and UFS and etc. So we're already generic with respect to the models. Now, when we designed the system, the models, we had a list of a dozen models, and we expect a new model would come in every 5 or 10 years, but models take a very long time to develop. So the interface, it was still a bit of work to develop an interface. So we went back to the drawing board, and we are in the process of really simplifying the interface so that if an AI model comes every week, we can put them in as they come as fast as possible. So that's coming, and that's going to be the first thing we do with AI. Then we look at how can we use AI inside the data assimilation itself. There's a lot to do there. There's some obvious things about quality control. AI maybe could be better than humans, looking at billions and billions of observations to sort out which ones to use and not to use, etc. There's a lot of things we can do there. First thing is going to be, are AI models good enough for data assimilation? Typically, how do they compare against observations? Typically, these AI models have been trained against reanalysis, fairly at some kind of medium resolution. They look at 5-day forecast quality, but that's not, for data assimilation, you need very good short-range forecast, and you need, you don't want a 200-kilometer resolution. You have your observations at much higher resolution. All kinds of the observations also see variables that these AI models typically have not been trained on. So that's the first thing we are going to do when we started here comparing. We run a forecast and we run different metrics and we compare for the different observations how well these models can reproduce these observations. So we are putting that in place. I won't tell you which model is the blue and the black, but we're starting here to put that in place. And that's going to be the first step towards using this model in data assimilation. If a model is completely useless at reproducing what observations can see, there's no way you can use it in data assimilation. So that's what we're starting to do. Here again, we are going to look at different metrics. We're putting that in place, but that should be a nice tool once we have it. Okay, so I'm going to stop here and take your questions. Thanks for your attention.
Does anybody have any questions for Yannick? Let me know if any show up online. So I'll start. I had one question, so the YODA database, you show a plot of bringing all the different types into that. Is it restructured and reformatted into something that's common there? Because we have a data commons project that we're looking at that observations will be a part of it. I've looked at data assimilation kind of as a guide because these systems have to bring in observation types from all over the place and harmonize them typically, so.
Yes, so YODA really there's two elements. There's one element that's in memory, storage, and handling of things, and that's fairly mature, although we are still improving it a little bit, but that's done, and there is basically one model that handles everything. And it's also supporting a restricted number of file formats. So we have our own file format, which is an SCDF with some structure in it, and it's just not any SCDF, but we've put some structure into it. Mm-hmm. We're also capable of reading and writing ODB files and some buffer files, not all of buffer. It's a bit messy, so we can handle some buffer files. But originally the idea was to have only one file format, but it got a little bit challenging. Not everybody at the different agencies could agree on one format to use. So we're supporting these 3 different formats. But in memory, it's uniform. There's only one data structure to handle all the observations.
Okay, so it comes in multiple types of formats. That was kind of my question.
Yeah, we reduced it to 3, which is a lot less than what's out there.
All right.
And internally for our testing, we are only using the NetCDF format. Mm-hmm. It's only the agencies. So MetOffice is using ODB, NOAA is using Buffer.
Right.
But we don't all our R2D2 is only running netcdf files.
Got it. Okay. Go ahead.
Thanks, Yannick. Very interesting talk. I have two questions. The first one has to do with coupled DA. You mentioned that there's some work now ongoing to for coupling B, essentially. I think this is one of the most hardest problems in DA because you're doing work on the interface between two different systems that have different time scales. So can you say more on what kind of research is being done on that front? And the second question is, you mentioned when going to AI models, you had to simplify the model interfacing. Can you be more specific?
Okay. So for coupled B, it's very early. We're starting something. It's actually on pause now because, as you know, half of our staff is on furlough, so that's on pause. But that's really early. We don't have a final answer how we're going to really do that. We're just starting. So the coupled HRX is easier. Coupled solver is actually not that difficult, but the coupled B, yeah, that's a tricky one.
That's the meat.
Yeah, that's going to be the difficult part. So I don't know yet. And the interfacing, yeah, we basically the original interface with the models was really leaving the responsibility of allocating, storing data to the models. And we are really taking that over and implementing it into JEDI, so we can control the memory. And basically what we need to right now to interface models is I/O, so that we can read their files, put them into a memory that we control, and then being able to pass to the model the fields they need to when you want to run the model. We want to do everything in core. We don't want to go for files when we call the model. So we have to be able to pass back to the model and fill in whatever memory layout they expect. But once we have these two things, the I/O and being able, we are taking ownership of the memory really, and that's actually what makes JEDI itself a little bit more complicated because we have to handle that memory, which we were not before. But it's really for people who come in with a new model, it's a lot less work. Especially, with models, now we have models in Fortran, in C++, and in Python. So that's also, that was, to delegate the handling of memory to Python was very difficult. So we're keeping, we own the memory now in JEDI.
Any other questions? So when you started this project, you mentioned that you had some software you based it on, OOPS from ECMWF. Did you have a framework is that what JEDI is built off of? Because then you talk about legacy code in Fortran and, modernizing code, so it's modular, built on C++, easy to configure, easy to run in a generic way. Did you have something you were building that based on, or is this all from scratch, I guess?
So OOPS is something we started at ECMWF just a few years before I moved here. Mm-hmm. So it was new software. It was not legacy code from.
Okay.
So we took that. We discussed actually whether we should. So OOPS written in C++, whether we should use it directly, and it has evolved over the last whatever it is now, 6-7 years. It's not looking at all like the original version that was at ECMWF. We discussed, should we keep with that? Should we rewrite from scratch in Python? At the time, operational agencies didn't want Python in their operational runs, mm-hmm. so that was not an option. So we stick with C++, and then it might as well start from OOPS. OOPS is not big at the time, especially. I think it was maybe 15 or 20,000 lines of code. Compared to these DA systems that are millions of lines, it's really small. So we started from that, but everything else pretty much we rewrote from scratch.
Okay, I was just curious because there's a lot of modeling efforts where they're looking at some of those types of challenges, working from legacy Fortran and newer, modern, more modular, more generic ways of doing things. So.
Yeah, I remember when MPA started, we almost did it in C++, and I'm disappointed we didn't. Mm-hmm. That's where it went. I think, there's some really good design ideas that could be taken from this and applied to the model, to handle different elements inside the model, and you could do that with a nice. There's lots of things you can do in C++ that you can't do in Fortran. But usually people who work in this field, they only know Fortran, so they don't think what you could do if you had different language.
Right. But I think new, early career aren't necessarily taught Fortran, so that's also a challenge if you keep things in Fortran. And then also migrating to GPUs and whatnot, so.
Yeah, we've had people in interviews, we asked if we were using Fortran, and when we said no, it's C++, we said, oh good, I wouldn't have taken the job if it was Fortran. So yeah, younger people is much easier to bring on board because then you're not stuck. It's very difficult to sell your skill in Fortran if you look for another job. C++ is a little bit easier.
All right, any final questions or thoughts, anything online? Okay. If not, yeah, anything you look like, okay. All right, we're good. Thanks, Yannick, again.